Yes, so the error in the Simpson rule was given by minus h raised to power 5 divided by 90 times the fourth derivative of f evaluated at some eta, where eta is a point lying in the interval AB, right? And then further, we also obtained the composite Simpson rule. So basically, the idea was that if your h is very large, right, or maybe the f is not close to a cubic polynomial, right? It can be any arbitrary function. Then your error is, if you use directly this formula, that is directly the Simpson's rule, the error is going to be large, right? This means that the approximate value which we are getting in I2F, that is not going to be very close to the IF, right? So the idea is that you can divide the interval into a sub-intervals, and then on each of the sub-interval, you can use the Simpson rule. So upon taking the subdivision of the interval AB into n sub-intervals, starting from x0 up to xn. So we have an equally spaced point with h is equal to b minus a divided by n, right? And n is taken to be even. So then we obtain the formula for the approximation of the IF as so h is the distance between any two consecutive points divided by 3, and evaluation of f at the x0. And then, so we will be applying the, so you have to see that you will be approximating the function by a quadratic interpolating polynomial. And then for that, you need 3 nodes, right? So we were using the 3 consecutive nodes. So that's how we had got the formula as this. So I'm going to write the last 3 terms. So this is going to be f evaluated at xn minus 2 times 2 plus 4 times f evaluated at xn minus 1 plus f evaluated at xn. Right? So this is a composite Simpson rule. And we also obtained the error in the composite Simpson rule. Which was given by minus h raised to power 4 b minus a divided by 80 . Okay, so we had obtained it as a summation, which we could get the upper bound on, right? So if I write this as, let me write in this way. We got it as h raised to power 5 divided by 90 into summation of fourth derivative of f at some eta j, and j is varying from 1 to n by 2. Right, and using this, we found the upper bound of this term. That is, we can bound this by the maximum, and then that way we could get the upper bound of the ENF, right? So let me give you the equations, these as equations number, because I will be requiring them further. So 1, 2, 3, and 4. And of course, we also obtained the, so these were the parts of the Newton-Cotes formula, Newton-Cotes closed formulas, right? And then we also saw some of the Newton-Cotes open formulas. So that the rule which we discussed was the midpoint rule. And as I mentioned, that there are other rules also which can be obtained as a part of the open Newton-Cotes formula. So it's the same idea, like we are approximating the functions here by the interpolating polynomial, including the endpoints, right? Now you can take 2 point, for example, if you want to approximate, you want to get a Newton codes open formula by approximating f by a linear interpolating polynomial. So only thing is that you have to choose the points inside the interval. So for example, if you take in the triple rule, we approximated the function f by a linear interpolating polynomial by taking the nodes as a and b, right? Now instead, if you take two equally spaced nodes inside this interval, so I'm dividing this whole interval into three equally spaced subintervals, then you can call this as x naught and this is as x1. And you write down the interpolating polynomial by taking nodes as x naught and x1. Okay, and that way you will get by using this interpolating polynomial in approximating fx, you can obtain the integration rule, and that will be a Newton codes open formula. Okay, because it does not involve the endpoints. So the idea remains the same, but thing is that these formulas which we have discussed, that is the closed formulas, they are most used one. So that's why we have discussed in detail, but you can derive any other formula by using the same idea. Only thing is that you have to see which nodes you are going to use. Okay, so overall what we have been doing, let's just get an idea that we have approximated fx by a interpolating polynomial. Right? Now, this interpolating polynomial, you can design, you know it for any general degree n, right? So you can, according to the need, you can design it. Let's say we have the interpolating polynomial at the nodes x0, x1 up to xn, right? So we know that let's call it p and x. So we know what p and x looks like. It is nothing but, I can write it as in terms of the Lagrange basis polynomials. So Ljx times f at xj. J is varying from 0 to n, right? So all the integration formulas which we have obtained so far to approximate this, they are of this form. So it is of the form wj f at xj, right? J is varying from 0 to n. And you can realize these wj's are nothing but integral of Lj of the x over the interval AB, right? So these wj's are basically, they are called the weight function. So what we have been doing, we have fixed the node. That is, we know that the nodes are going to be x0, x1 up to the xn, and then we are basically computing the weights, which are wj's, by using the interpolating polynomials. So basically, we are just integrating the basis polynomials, right? And that's how we could obtain the weight. Now, there's another way to obtain these weights. Like, we are not going to integrate this basis Lagrange basis polynomials. We are going to use another approach. And this method which we are going to use, this is called the method of undetermined coefficient. That is the same formulas which we have obtained so far. They can be used by using this new method, which we are calling it method of undetermined coefficients. So let's see what do we do in this method and how can we obtain, like what differently we can do to get these weights wj's. So what we are going to do, so for a fixed set of nodes, we are going to determine the weights by imposing the conditions that the resulting rule, that is a integration rule, whichever we aim to have, that rule is exact for polynomials of degree less than equal to n. Okay, so we have a n plus 1 nodes, and then we want to determine these n plus 1 weights. And then how we are going to determine these weights? We are going to impose the conditions that the whatever the integration rule we are seeking here, which is this rule here, this is exact for the polynomial of degree less than equal to n. Okay, can you tell me what is the meaning of the exact here? When I say that this is
No error.
yes?
No error.
No error, right? So this means that when we will find so if you call this rule as I tilde of the f, and this is if, this means the exactness means that if I compute the error between the integration rule which we have got and then the exact integration value, the value of the integral of f over the same interval, then this is going to be 0 whenever f is a polynomial of degree less than equal to n, right? This is the meaning of this sentence, that the rule is exact for the polynomial of degree less than equal to n. Okay, so now let's take one example and try to see how this really works. Okay, so I'm just going to explain it for one set of nodes, and then you can try to derive it, use this idea to derive any of the rules which we have discussed so far. So let's try to find the weights W0, W1, W2, such that the approximate formula which we are using to approximate the integral of f over the interval AB as this. So we want to have it as W0 times the nodes. I'm taking it as A, and the midpoint A plus B by 2, and then the other endpoint, right? So 3 nodes I'm using here. So nodes are fixed. So nodes here I'm taking it as the midpoint A plus B by 2, and the endpoint B. Okay, and what we want to do, we want to determine the weights W0, W1, W2. So this rule is exact. So we want to have these weights such that the approximate formula is exact for all polynomials of degree less than equal to 2. Okay. So note that this is equivalent to say that, so if I call this as equation number 5, so it is equivalent to say that is equation 5. This is exact for, okay, so we want this rule 5 to be exact for the polynomials of degree less than equal to 2. Any general polynomial of degree less than equal to 2. So can you tell me that like which polynomial I should test it with, so that if I have it, so okay, if we can test it with just the basis polynomials, right? For the P2 we know that there's a basis. So if we can just test this rule for the basis polynomials, And if it is exact for them, it is going to be exact for any general polynomial, right? So which polynomial I should test it here? So tell me if you agree with me. So I'm going to just test it with fx is equal to 1, x, and x squared. Will that suffice?
Yes, ma'am.
Yes, ma'am.
So let's do that, because if you have the rule is exact for these three these three 1, x, and x squared, then you can write any quadratic polynomial as a linear combination of these, and that will be true for any general polynomial also. Okay, so I'm just going to test it with these three functions. So now let's take fx is equal to 1, x, and x squared in 5. What do we get? So let's take fx is equal to 1 first. So the right hand side, the left hand side is going to be this, and the right hand side is going to be W0. The f is constant, so we will get W0, W1 plus W2, right? And we know that the rule is going to be exact for this. That's how I'm going to determine my Wi's. So this is going to be equality. Okay. Likewise, we will have that integral of x dx. This will be W0 a plus W1 a plus b by 2 plus W2 b. And the third equation which we will get, that is going to be integral a to b x squared dx. This is going to be equal to W0 a squared plus W1 a plus b by 2 squared and W2 b squared, right? And if you simplify this, this is nothing but b minus a, and this is going to be b squared minus a squared divided by 2. And if you simplify this, this is going to be b cubed minus a cubed divided by 3. Okay, so here W0, W1, W2, these are unknowns. So 3 unknowns and 3 equations. So you will be able to determine Wi's uniquely. If you can have the determinant of the matrix, you just try to write it in the matrix form and try to find W1, W2, and W2, W1 and W2, right? And upon solving, so I'm not really going to solve this. So you can just simply apply the Cramer's rule and you can solve it. So what you will get? So we'll get W0 as b minus a divided by 6 and W1 as 2 by 3 b minus a and W2 as b minus a divided by 6. Okay, so what is going to be the rule? So we have got the rule as the approximation of a to b fx dx. This is nothing but, so I'm going to substitute here and I'm going to take out the factor b minus a divided by 6. Okay, so b minus a divided by 6. So I'm going to get f of a plus this will be 4 times f evaluated at a plus b by 2 plus f of b, right? And I think you're already familiar with this rule, right? So this is nothing but Simpson's rule. Right? So this is how this method of undetermined coefficient works. That you, given the integration rule, you just try to determine the weights so that that rule is exact for certain polynomial degree of certain order, right? Okay, so we have been talking about this exactness for the polynomials, right? So there's a formal name associated with it. It is called the degree of precision. So let me define it formally. So this is the definition. So a numerical integration formula let's denote it by I tilde of the f that approximates the exact integral if. This is said to have degree of precision m if the following happens. So we need two things. So first of all, I tilde f should be the same as if, that is the approximate value, and the exact value, this would be same for all polynomials fx of degree less than equal to m. Okay, and second requirement is that the rule is not exact, that is I tilde f is not equal to if for some polynomial f of degree m plus 1. Okay, so is the definition clear? So
Yes.
what is going to be the m for trapezoidal rule? What is the degree of precision for the trapezoidal rule? It's 1, right? Because you can check the from the error itself we had obtained that the trapezoidal rule is exact for the polynomial of degree less than equal to 1. And now if you want to check whether this I tilde f is not equal to if for the polynomial of degree less than equal to m plus 2, m plus 1 is going to be 2, you simply take fx is equal to x square. Okay, now you can compute the value of this integral, right? So this is going to be if. So you can compute the if, which is going to be integration a to b x square dx. And then you want to check that it is not exact equal to the I tilde of f, which is going to be b minus a divided by 2 fa plus fb. So you can choose a suitable interval a to b, and you will be able to check that these two values are not equal. Okay, so the degree of precision for the trapezoidal rule is 1. And now what happens with the Simpson rule? What is the degree of precision for Simpson rule?
2, ma'am.
Recall the error
3.
formula.
3, ma'am.
So if you see in the error,
3.
if you notice, we could obtain the formula, like if in the method of coefficients, we have obtained the Simpson rule itself, right? So we are approximating the function by a quadratic polynomial. So of course, the initial expectation is that, of course, the rule is going to be exact for the quadratic polynomial. But then if you just try to recall how did we derive the error formula? So we had performed that this W function, which was playing role. Because of that, we had got an additional degree of the accuracy. So we could get that the integral, like you had performed the integral mean value theorem. So finally, what we had got is that the fourth derivative of the f, right? Because of the structure that the error has. Okay, so in the Simpson rule, we have got an additional degree of accuracy. It's not just exact for the quadratic, it's exact for the cubic. And this will happen for all the integration rule which you will obtain by taking n to be an even number. Okay, so the whatever you just try to look at the proof of the error formula. You have to define a function w, and that you have to perform an integration by parts, and then integration by parts give you basically one additional derivative on the f. Okay, and that's how you get one additional degree of the accuracy. So if you take n to be any even number, the same phenomena will happen. Okay, so for n even, you will get an additional degree of the accuracy for these integration rules. Okay, so now let's look at the error formulas again. Okay, so I'll start with the trapezoidal rule. So we'll make an observation. So let's consider the error in the trapezoidal rule. So can you tell me what was the error formula we had obtained for simply the trapezoidal rule?
Minus of b minus a whole cube divided by 6 into f double dash hi.
I think it was 12 or 6. It was 12, I think.
12. Yes, ma'am.
And f double prime at some eta. Eta is in the interval AB, right? And if you look at the composite trapezoidal rule, so what is the error formula we got for this? So we had got it as minus h cube divided by 12 summation f double prime at eta j's. J is varying from 1 to n. So this is considering that we are taking this as a subdivision of the interval AB. So we start with x0, x1, and the last point, which is xn. So h here is nothing but b minus a divided by n. Okay. So here, of course, we had just one unknown, right? Eta is any point in the interval AB. And we can further simplify this term. So let's see how we are going to simplify it. So I'm going to multiply by n and divide by n. So I write it as 1 by n, j equals 1 to n, f double prime of eta j. So n is here, the number of subintervals. Okay, and this is the length of each of the subinterval. Now, if I call this quantity as m, that is m, I'm calling it as 1 by n, summation j equals 1 to n, f double prime of eta j. Okay. So tell me if you agree, if I say that this is always less than equal to maximum of f double prime of x over the interval AB.
Yes, ma'am.
And what is going to be the lower bound? Like we have an upper bound, we can also have the lower bound, right? This is assuming that f double prime is continuous. Okay, that is f is twice continuously differentiable. So that's the assumption we have it. So this is greater than equal to, if you find the minimum value of the f double prime of x over the interval AB. Okay, so now can you say something about this quantity now? So This M is basically lying between the maximum of the f double prime of the x and minimum of the f double prime of the x. You can treat f double prime of the x as some function gx. Okay, so we have a minimum. So sorry, this M is the value lying between the maximum of the g and the minimum of the g. So can you use the integral mean value theorem and say something? Sorry, integral value, intermediate value theorem, not the integral mean value theorem. So can you use the intermediate value theorem to conclude something from here?
There exists a point C between A to B such that GC equal to F double dash C. F
Yeah.
double dash X.
We are assuming that f double prime is continuous function, right? And this M is a value between the maximum of this function and the minimum of this function. So there has to exist one point in the interval AB where this value will also be attained, right? Since f double prime is continuous, on AB by intermediate value theorem, it must attain all values between its maximum and minimum at some point, which means that there exists some eta in the interval AB such that f double prime of eta equals m, right? So therefore, what can I write? So this error formula, which is ENF, this will basically become, so this quantity is nothing but m. This is nothing but the f double prime of the eta, and then we have this vector. So this is minus h cube into n divided by 12 into f double prime of eta for some eta is in the interval AB. So upon simplifying, so n into h is b minus a. So this is going to be minus b minus a divided by 12 h square times f double prime of eta. Right? So this is upon simplifying, we have got this, and we could see that again we have got the error in terms of the evaluation of the second derivative of f at some point which exactly is not known, right? We just know that it is some point in the interval AB. Okay, so likewise, if you apply the same trick for the composite Simpson rule. So first of all, for the Simpson rule, we simply have, so let's write down. So for the Simpson rule, we have that the error is given by, so we already gave it as an equation number. This equation number 2, right? So this is minus h raised to power 5 divided by 90, and the evaluation of the fourth derivative of x at some eta. Eta is in the interval AB, right? And for the composite Simpson rule, we can simplify as in the case of the composite trapezoidal rule. So here the error formula is minus h raised to power 5 divided by, so let's write it down. So where it is. So h raised to power 5 divided by 90, and then we have summation f double prime at eta j, the fourth derivative of the f evaluated at eta j. J is varying from 1 to n by 2. Okay, you apply the same trick here. That is, what factor you have to divide and multiply here? N by 2, right? So you take the factor 2 by n here and multiply by n by 2, right? And then for this factor, you use that that we are assuming that f is 4 times continuously differentiable. So this will be equal to sum f double prime of the f, the fourth derivative of f evaluated at some eta, right? So upon simplifying, what we will get? We will get ENF as minus h raised to power 4 divided by 180 times b minus a into f prime, sorry, fourth derivative of f evaluated at some eta. Okay, you have to verify from here to here. Okay, fill that this is what we get. Okay, so let's give these equations. These are the equation numbers. So we have 4, 5, 6, 7, 8, and 9. Okay, so now you look at these four. So this is just, I have considered the trapezoidal and the Simpson rule, but any of the Newton-Cotes formula you will consider, you will be able to write the error in this form, right? That you will be having the evaluation of some derivatives of the function at some unknown points in the error, right? So since we do not know eta exactly that which point it is, so this is actually, we can just get some idea of the error that, okay, this is going to be of this order. But since we cannot really compute the exact value of this, the error formulas, which is given by 6, 7, 8, and 9, right? Because it depends on some unknown points eta in the interval AB. Okay, so now we are going to see another error formula, which will not have the evaluation of the derivatives of the function on the unknown points. Okay, and this is called the Peano kernel error formulas. So I'm just first going to explain it for the trapezoidal rule, and then we will see it for the other rules. So let's consider first for the trapezoidal rule. We understand the idea, and then we can apply it to any of the integration rule. Okay, but for that we need the understanding that what exactly the error looks like in these formulas. So for example, if we talk about the standard trapezoidal rule, we know that this is how the error looks like, right? So from here, at least one thing I can conclude, that this is exact for polynomial of degree less than equal to 1. Because we have the f double prime eta sitting here, right? So this is the information is going to be useful for us to derive this Peano kernel formula. So now what assumptions we are going to have on the function f? So I'm going to assume that f is continuously differentiable. That is, I'm assuming that the first derivative is also belonging to it's also a continuous function over the interval AB. And for the second derivative, I'm not assuming that this is a continuous function. Only thing I'm assuming that this exists and this is integrable on the interval AB. So this is slightly weaker assumption than what we have in the starting, right? But we can of course work with the whatever the assumptions we had before on the function f, but I'm just slightly reducing the assumption on the f here. So what we are interested in finding the error formula, right? Which basically should not depend on any of the unknown parameters. So here, what is going to play a crucial role is the Taylor's theorem. Okay, so let's recall the Taylor's theorem. So I will require it the Taylor's expansion with the remainder term in terms of the integral. So I can write any function fx, which is, so let's assume that this is n plus 1 times differentiable. So you will be able to write this as a pnx plus rnx, where pnx is nothing but, tell me what it is going to be. So this is, I'm calling it as a remainder term, right? And I'm calling that this is going to be a polynomial of degree less than equal to n. So what this will be? You have to expand it in the neighborhood of, say, x naught.
f of x naught plus m dash plus x minus x naught by 2 factorial 1 factorial f dash x naught plus
Right. So it will go up to, the last term is going to be x
n minus 1
raised to power n divided by factorial n, and nth derivative of f evaluated at x naught. If you pay attention, this is actually a polynomial of degree less than equal to n, right? Because the f evaluation is actually at some point only, right? So what is the factors which are contributing? Is nothing but the x minus x, the powers of the x minus x naught. So this is basically a polynomial of degree less than equal to n. And what is the Rnx in terms of the integral form of this? So this is 1 by factorial m integral x naught to x minus t raised to power n f n plus 1 t dt. Right? So this is a remainder term. Okay, so I'm going to use this. So this is just the general form. So now I can apply it for our purpose. So using Taylor's theorem, how can we write so I'm going to use this information that this Taylor's trapezoidal rule is exact for the linear polynomial. Okay, so I will break my function fx as a linear polynomial plus some remainder term. You will see in a minute why I'm just taking the approximation by the linear polynomial. Okay, so I'm taking the expansion in the neighborhood of the a, so where this p1x is going to be f evaluated at a plus x minus a and the derivative of the f at a. Okay, and r2, which is a remainder term, this is going to be integral from a to x minus t f double prime t dt. Okay, so we have this information. So if I consider the approximation of f using
मैम x minus t square आएगा.
x minus t square, no, we have x minus t raised to power n, right? Recall, when you will apply the integral mean value theorem, you will have this factor outside, and then when you will integrate this, you will get x minus t raised to power n plus 1 divided by n plus 1. So that's how we get the usual term. So we have to have 1 power less inside the integral, because there will be integration happening that will give you 1 extra power of the.
Okay, ma'am. Yes, ma'am.
So we have one, so this is what the remainder term is. Now what you have to realize,
Ma'am, in Taylor's theorem, Pnx Pn minus 1x नहीं होगा.
where?
Uh,
Here?
ma'am, yes, ma'am.
Which?
Fx equals to Pn minus 1x plus Rnx.
No. See, Pnx, I'm taking it as a polynomial of degree less than equal to n. So you can see here I'm writing the highest power it is going is up to n. Okay. And the remainder term, if you will just try to simplify this, so what you will get? So if you try to apply the integral mean value theorem in a stable way, so you will get this remainder term as x minus x naught. Upon simplification, I'm directly writing it fn plus 1 at some j. Okay, so you will use the continuity of the fn plus 1 to take out this factor, and then you will have the integral of this only the polynomial, which upon simplification will give you this. Okay, so the Pn is a polynomial of degree n plus 1, so the Rn will have the power 1 higher. Is that okay?
Yes, ma'am.
Okay, so again, what is our interest is the error in the trapezoidal rule, right? So first realization you have to make. So if I denote the error by E1, so you have to make this observation. So we denoted the error formula by E1. So E1 of, if I take any two functions, let's call it f and g, which are sufficiently smooth functions so that my error formulas are making sense. Okay, then the error of f plus g is going to be the same as error in the function f using the trapezoidal rule plus error in the function g using the trapezoidal rule, meaning that the error function E1, this is linear. So what should I do to realize this? You just look at the error formula, the step where we had really derived the E1f. So it was that we were integrating the interpolation error from A to B, right? And the interpolation error was x minus A into x minus B and f a dx dx, right? So use this to observe that if you consider the error in the function f and error in the function g, then the error in the function f plus g is going to be the same as error in the function f and error in the function g. So only thing is that you have to realize that what is happening with this divided difference, right? So will you be able to check this? That this error function is linear? Is it clear what I'm trying to convey here?
Yes, ma'am.
So you just substitute here. Here you take E1 of the f plus g, where f and g are two functions, where you are trying to find the approximation error using the trapezoidal rule, and which is going to be use this formula, and then you find what is E1f and what is E1g, and you will be able to realize that both are going to be same. Okay, just verify this. So now we have got that my error function, this is the linear function. So I'm simply going to use this equation. So if I call this as a star, therefore, using star and linearity of the error function E1, we have that E1 of f, that is error in the function f, is nothing but the error in the P1 plus the error in the function R2. So note that here everything is a function of x. I'm not writing it. So f is a function of x, P1 is a function of x, R2 is also a function of x. Is it okay? Now what is happening to the even P1, the error in the P1?
Zero.
So this is where I'm using that recall the error formula. So the exact error formula which we obtained using the previous analysis is minus b minus a cube divided by 12 f double prime evaluated at some eta. Right? This is what the formula we used. So if you use that for P1, you will have the second derivative of the P1. So this is going to be a zero quantity. Okay. So what we are left with, that E1 of f is nothing but E1 of the R2. And now I am going to use the actual definition of this error, which is what is the E1? E1 is nothing but IF minus I1F. Right? So I'm going to use this here. So this is going to be I of R2, which is integral a to b R2 dx minus the approximate value using the trapezoidal rule. So which is going to be b minus a divided by 2 R2 evaluated at a plus R2 evaluated at b. So is it okay so far?
Yes, ma'am.
So
Yes,
now
ma'am.
it's just a simplification. We are almost through. So now we just have to simplify the things. So we already know what the function R2 is. So this is a function of x. So let's substitute here. So R2 is given by this. So this is integral a to x minus t, f double prime t dt, right? Minus b minus a divided by 2 R2 at a. This means that I have to take x is equal to a here. So what will happen to the R2 of a? What is R2 of a?
Zero.
Zero.
Because you will get limit from a to a, right? And R2 of b is going to be limit from a to b and then this factor. So R2 at a is 0. So R2 at b is integral a to b. X is equal to b, I have to substitute. So this is going to be b minus t, f double prime t dt. Okay. So note that here, let's try to just focus on this integral. Sorry, we will get one more variable here, dt dx, because there was an integration with respect to x already existing here, right? So let's just focus on this integral. So this is the integration in two variables, t and x. So let's call this is x is, so we have first the limits of the t is varying from a to x, and then x is varying from a to b. So let's try to draw this region of the integration. So we have the line, say, so let's take this as a t-axis. This is as x-axis. So these are the lines t is equal to a, t is equal to b. And here you will have the lines x is equal to a and x is equal to b. So we have to see what is this region of the integration here in this integral. So t is varying from a to x. Right, so I also have to have a line which is t is equal to x. So which is going to be something like this. Right, this is a line t is equal to x. So let's try to understand. Now we will get, so we have to see whether this is the region of the integration or this is the region of the integration. So let's try to see. We are having the limits of t from a to x. So t is varying in this direction. So I have to take a strip parallel to the t-axis. So if I take here, so this is going to be from x to b, right? So this is not the correct thing. I have to take the strips from here. So this is from t is equal to a to the t is equal to x here. and then my x is varying from a to, sorry, these strips will be varying from x is equal to a to x is equal to b. So this is my reason of the integration in the first term. Okay, so now you try to notice here in this integral, t is coming in both the terms, like f, we are having the evaluation of the f double prime at t, and in this term also we are having t, but x is coming only in this polynomial factor, right? So if I do a change of variable, then I will be able to simplify my things, right? Because I can simply integrate with respect to x first, and then we do it with respect to t. So that's what I'm going to do. I'm going to apply the change of variable here. So which will lead us that this integral, let's just focus on this integral first, a to b, a to x, x minus t, f double prime t, dt dx. If I do the change of variable, that is, first I want to integrate with respect to x, and then I want to integrate with respect to t. Okay, the function remains the same. What will change? The limits, right? So what are the limits of the x? Can you tell me? So this is my region of integration. So if I check the limits of the x, so I have to take a strip which is parallel to the x-axis, right? So this is varying from x is equal to t to x is equal to d,
B.
right? And then the t is going to vary from a to b. Okay. So now I can very well integrate with respect to x, because x is arising only in this term. So this is going to be a to b. I can keep f double prime t outside of this integral. And we can simplify this term. So this, you can simply integrate it, and I'm directly going to write what is the final value I will get upon integrating. So this will give me t minus b square divided by 2. Okay, so basically I have got this value as t minus b square divided by 2 f double prime t dt. Okay, so therefore I can just go back to this step here. So E1 of f, this is going to be, I'm just going to substitute here this integral value. So this is integral a to b t minus b square divided by 2 f double prime t dt. And then here the second term is minus b minus a by 2 integral a to b of b minus t into f double prime t dt. Okay. So now note that these both the integrals are over, they are having the limits as a to b, and f double prime t into f, this term is common in both the terms, right? So I can simply write this as, so what I'm going to get it here, t minus b square divided by 2 minus b minus a times b minus t divided by 2. So we can simplify this. So I'm going to take out the factor t minus b by 2. 1 by 2, I'm going to keep it outside. And then if you simplify, you'll get t minus b minus plus b minus a. So this will be t minus a times f double prime t dt. Okay, so if I denote this factor t minus b t minus a divided by 2 as a new function, let's call it as kt, then this is nothing but integral a to b f double prime t into kt dt. Okay, so note that this is again a polynomial, right? And in this formula, basically we have obtained it in terms of the integration of the so you have, if you really want to compute the exact iteration, you really have to integrate the second derivative of f multiplied by this constant, this polynomial. Okay, so this is how the things happens in the case of the trapezoidal rule. Now let's try to use the same idea and try to simplify what happens in the case of the composite trapezoidal rule. So underlying idea remains the same. So I will be writing f Okay, so let me directly write the error formula. So you will be mimicking the same steps what we have done here. Okay, but it will be happening on each of the subintervals. All right. So on each of the subintervals, you're going to have the approximation of f by a linear polynomial. So when you will use the Taylor's expansion, you will end up getting the same steps up to here. But what is going to be the E1 in this case? Or let me call it as ENF. So this will turn out. So you have to fill in the previous steps. So E and F will be En of R2, and what is a exact error in the composite trapezoidal rule? It is IF minus INF. Right? So basically here we have to simplify En of the R2, which is going to be integral A to B. Same idea. What we have done here, now we will be doing it for each of the subinterval basically. So we will have a more terms in this En of the R2. So this is again going to be the same term. But then here I will have In of F, In of R2. So In of R2 is R2 evaluated at x0 plus 2 times R2 evaluated at x1 up to R2 evaluated at xn minus 1 plus the last term is going to be R2 evaluated at xn. Okay. So the setting is the same. We have the interval AB, which is divided into n subintervals with equal length. Okay. So this is how we will end up. So is it okay? So do you all agree with whatever we have written here? Will you be able to obtain this step?
Yes, ma'am.
Okay, so you have to fill
Yes,
in the
ma'am.
further steps which I've left here. Okay, but it's just mimicking the previous steps which we have done in the case of the trapezoidal rule. So what remains is to further simplify this, that what happens to this term. So let's again substitute what R2x is. Okay, we know that x0 is A and xn is B. So let's substitute that first. So we have this is as R2 x dx minus h by 2, and h here is nothing but b minus a divided by n. So R2 at x0 is nothing but R2 at a, and the last term is R2 at xn. So this is going to be R2 at b. And then we have the terms 2 times of R2 at x1 up to R2 at xn minus 1. Okay. Now I'm just going to substitute the expression for the R2. So this is going to be a to b, a to x, x minus t, f double prime t, dt, dx, minus h by 2. R2 at a is 0 again, right? And R2 at b is going to be a to b, b minus t, f double prime t, dt. And then let's write down the other terms. So it is going to be 2 times. So the first term is going to be, so we have integral from a to x, and then we are substituting x is equal to x1. So this will be a to x1, x1 minus t, f double prime t dt. Next term will be a to x2, x2 minus t, f double prime t dt. And likewise, the last term is going to be a to xn minus 1, xn minus 1 minus t into f double prime t dt. Okay, so I've just substituted the expression for the function R2. So note that this further I can apply the same step. That is, I can change the variable here. So using change of variable as before. So that is, I will change the order of the integration. So this is going to be a to b. These are the limits for the x, and then the limits for the t is going to be t2. Sorry, limit for the x is going to be t to v. Okay, x minus t dx. I can do this integral separately, and then f double prime t dt. Okay, exactly the same steps what we have done before. And then we have minus h by 2. So the first term is also okay. I have the integral a to b, b minus t into f double prime t dt. Okay. Now if you try to pay attention to the second term onwards here, that is, we have integral from a to x1 in this term, and then we have integral from a to x2, and likewise the last term we have an integral from a to xn minus 1. Okay, so the integral, the limits of the integration are different on each of these terms. Okay, now I want to use some idea so that I can write this limits of the integration as a to b itself, so that I will be able to combine the things here, right? So I'm using this this notation. So I'm defining this xj minus t. So if you are already familiar with this positive part of the function, then it's great. If not, then let me define how it works. So this is nothing but, so this is xj minus t, and in the subscript I'm using this positive sign. Okay, so this function is such that it is going to take the value xj minus t itself if xj minus t is positive. Okay, and it is going to take the value 0 if xj minus t is less than equal to 0. Okay, so we can define this for any j So I'm going to use this notation xj minus t plus, which is defined as this. Okay, so then my claim is, so if I use this notation and if we consider the integration from a to xj minus t f double prime t dt, so my claim is that this is a term which is same as, I can write this from integral a to b xj minus t plus f double prime t dt. Tell me if you agree with me. So this function, you just have to realize that this is non-zero only when xj minus t is positive, right? So this integral from a to b, you can break it in two parts, a to xj and then xj to b. So to realize this, what you just do, you just break this integral from a to xj minus t plus f double prime t dt, and then the other term will be xj to b xj minus t positive f double prime t dt. Now in this interval, what will happen to this function?
xj minus t.
In this interval, t is ranging from a to xj. So it is t is between a to xj, right? So xj minus t is going to be positive, right? So this function will be xj minus t itself. And what will happen to this value?
0.
0.
Right? So this is how you can realize that this is nothing but we have got back the same value which we already have. So this is, but using this notation, I can just write my integral in the with the limits as a to b. Okay, so this is what I am going to use for each of these terms. So this is going to be the same as plus 2 times integral a to b x1 minus t plus f double prime dt plus a to b x2 minus t plus f double prime t dt, and the last term in this summation is going to be a to b xn minus 1 minus t, positive part of this function. So this is basically, there's a name for this function. It is called the positive part of a function. So this is what we get. Okay, using this notation. Now, one thing you can notice in all of the terms now, that we have an integral from the limits of the integration is from a to b, and f double prime t dt is coming in each of the term, right? So this term again can be written as, so we have the first term is this and minus h by 2 integral a to b minus t. So I'm just combining all the terms here, right? So f double prime t is I'm factoring out from each of the term. So we will get this as plus 2 times x1 minus t plus up to xn minus 1 minus t plus. This everything gets multiplied with f double prime of t. Okay, so let's give it a question number. Okay, I think I lost track of the equation numbers. 8. Okay. So this is 9. Okay. Sorry, we had here also dt. All right. So now I'm just defining my function kt as integral from t to b x minus t dx minus h by 2 b minus t plus 2 times of x1 minus t positive part of this, and this goes up to xn minus 1 minus t positive part. So this complete thing, I'm calling it as kt. So I can write my integral as kt times f double prime t dt. Okay, and my claim is that this, upon simplifying, this kt is going to give, so we are going to get this expression. So this is going to be t minus xj minus 1 into t minus xj whenever t is in the interval xj minus 1 to xj, and j is varying from 1 up to n. Because note that if you take any of the point in the interval x0 to xn, which is nothing but the interval a to b, it will lie in any of the subintervals. Right? We have a partition of this whole interval into the subintervals. So you take any t in the interval AB, it will lie in one of the subintervals. Okay. So my claim is that if it is lying in the subintervals xj minus 1 xj, then the value of the kt is nothing but this. Okay. So let's just try to simplify this kt to observe this. So let's call it 11 and this as 12. So this is my claim. So let's simplify. Kt to really get that this is given by 12. So I'm not, see here we have a general n. So I'm just going to simplify it for n is equal to 2. And then the same idea can be applied to for any general n. Okay, so if we take n is equal to 2, then what do we have kt as? It is going to be integration t to b x minus t dx minus h by 2 b minus t plus 2 times. So note that n is equal to 2, meaning I'm just having one point in between. So this is x0, which is a, x1, and then this is x2, which is b. Okay, so I will get only one term here, which is x1 minus t plus. Okay, and note that h is b minus a divided by n is 2, and x0 is a, x1 is going to be a plus h, and x2 is b, which is nothing but a plus 2h. All right. So now we have to see. So this term is depending whether x minus t1, x1 minus t is positive or it is negative. So I'm going to see it as two cases. So the case one is when x1 is, when t is lying between x1 and x2. That is, I'm in this interval. So what will happen to the quantity x1 minus t positive? This is going to be
0.
Zero, negative 0.
this is 0. So my integral is reduced. So my kt is basically the integral from t to b, x minus t dx minus, so this term is 0, so I will have h by 2 times b minus t. Okay, and if you realize, this is nothing but what we have in the case of the usual trapezoidal rule. So this integral is nothing but t minus b squared divided by 2, right? And upon simplifying, what we have got is t minus b times t minus, so you will get t minus b plus h, which is nothing but t minus x1 divided by 2. Okay, so here I have used that x1 is equal to a plus h. So you just simplify this. Okay, so a plus h, so this is going to be same as b minus h. Both are same. All right, so this means that this, whatever the formula which we have written, so t minus, what do we expect when we are in the interval x1 to x2? So we expect t minus x1 into t minus x2 divided by 2. So this is what we have, t minus x1, and b is nothing but t minus, so v is x2, so this is nothing but t minus x2 divided by 2. Okay, so now let's see the case when t lies in this interval, that is x0 to x1. Which is x0 is a here, and this is x1. Okay, so in this case, x1 minus t positive part, it is going to be x1 minus t itself. So therefore, what is going to be kt? Kt is integral t to b x minus t dx minus h by 2 b minus t plus 2 times of x1 minus t positive part of this. So this will be x1 minus t itself. Okay. So note that this term we have already simplified in the case 1, right? So this is going to give me t minus x, t minus b times t minus x1 divided by 2. So now we have this term additional. Right, so I can just factor out t minus x1 here. So we will be left with the okay, we have a factor. So t minus x1 by 2 I can factor. So I will be left with t minus b and then plus 2h. Okay, and this is nothing but t minus a. So what we have got is t minus x1 and t minus x0 divided by 2. So is it okay? So thus we have that the error in this case is nothing but kt times f double prime t over the interval ab with kt as t minus xj minus 1 into t minus xj divided by 2 whenever t is in the interval xj minus 1 to xj, and j is varying between 1 and 2 here. Okay, so is it okay?
Yes, ma'am.
Yes, ma'am.
All right, so just one more simplification I will do. Like here we have got an exact formula, right? That is, we have the integral of this function times the f double prime t, the second derivative of f, and then you have to integrate it, right? And this function kt is called the piano kernel. So this formula is basically due to the piano. So that's how this name piano kernel formula. And this function kt, so you will see that we are writing So the simple triple rule and also the composite triple rule, we have got it in the similar form, right? It's just that KT is different in both the cases, right? So this is called the piano kernel, and this error formula is called the piano kernel error formula. Okay, so let's write down in the general case what we have got. So for general N, we have that ENF is integral a to b kt into f double prime dt, with kt as same given as above, which is t minus xj minus 1 into t minus xj divided by 2 whenever t is in the interval xj minus 1 to xj. J is ranging from 1 up to n. So we can get an upper bound also using this formula on the error En. So this is less than equal to, so this is a polynomial, right? So I can take its maximum out of the interval, right? So I'm just taking maximum of kt over the interval AB. So then what I will be left with is this. Okay, and this since this is like a polynomial, so its maximum can be found over the interval AB, right? And you have the idea of this, so you will be able to get the bound on the error En. Okay, so since it's the time, I'll stop here. If you have any questions here, I will take it in the next lecture.
Hello.
Right.
Hello, ma'am. Hello.
Yes, tell me please.
Ma'am, is it possible for you to shift our exam to 18? Like, ma'am,
No,
on
no, it's
16.
not possible to make any changes in the exam schedule. Okay, so the exam schedule is fixed, and I don't really want to alter anything because it affects a lot many other things. Because there are the presentations, project presentations, and other things are scheduled after 17. So it's not possible to really shift the exam. It will happen on 15 to 17. And the syllabus is going to be up to the interpolation. Okay, so this integration part is not going to be the part of the minor exam. All right.
We can have on 17.
But ma'am, we already have an exam on 16th Feb.
What are the schedule of the examination?
CSI and it, so
Sorry?
we have
The
exam
exam,
of CSI and it, so is it possible?
no, there's no possibility of altering the schedule of the examination because like I'm teaching other courses and I have to take the
So
exam
ma'am,
according to other course also. So, and then
so
we have a
ma'am,
presentation scheduled for the starting from the 18th. So there's no possibility to change the schedule of the examination. Okay. So don't
so
worry,
ma'am,
we have
what are the chances
sections.
of re-minor?
Why you're really thinking about the re-minor? You guys have studied well all the last, like from the last 1.5 months, right? You have been regular to the classes. No? So if you have followed everything well, don't worry, you're going to do good in the exam. Okay. And I'll drop an email with the exactly what I said with the syllabus, etc. Okay. Anyways, I have another class, so I have to disconnect the meeting now. All right.
Okay, ma'am. Thank you.
All right. Thank you.
Thank you, ma'am.